The topic for my final project is a case study in healthcare focusing on COVID-19. This notebook describes the analysis that's divided in two parts. The first is a correlation analysis of medical and non-medical data, and the second is time series forecasting of daily COVID-19 deaths. I will walk you through the code for each part of the analysis. First, we'll import all the necessary libraries, and then once that's done, we will go ahead and download the data from the Johns Hopkins GitHub repo. Once we have the CSV files, we'll convert them to data frames, and then we'll just view the data frames. So we have a column with all the countries, and then a column for each day since January 22, 2020, when the pandemic started. And we'll check what's the shape of this data frame. And once we've done that, we'll clean up the data frame. So we don't need the latitude and the longitude. So we'll drop those, and we just check the modified data frame, and it looks fine. The next step is to aggregate all the rows by countries. So in addition to countries, we're going to have like regions within the countries, and we are not interested in those for this project. So we are going to go ahead and sum everything to the country level, and then we just inspect the new data frame again to make sure that everything looks fine. We check the shape. So now we're ready to do some visual analysis. We're going to plot the cases for China, Italy, and Spain, countries that had very high COVID cases from the very beginning of the pandemic. And this is how that looks like. You can see that Italy and Spain grew exponentially, and China looks flat in comparison. Now we want to calculate an appropriate measure to capture the spread of the virus. So let's use China as a case study. So we'll plot the daily COVID cases, and then we will isolate the first 3 days from that plot. And next, we will take the derivative of that curve, which will give us the change in daily cases. And now this is how the graph looks like. So the next step is to estimate the maximum infection rate. So after taking the first derivative, we are going to apply the maximum function. And we can do this for China, for Italy, and for Spain. We can do the same thing for all countries by running a loop. So this is what we do next, and we'll save that variable in our data frame. Now we don't need all of the columns. The variable of interest is the maximum infection rate. So we're going to transform the data frame to save that variable of interest, and then just display the new data frame. So we're all good to go. The next step is to import our non-medical data, which comes from the World Happiness Report. We import the CSV file, display it to inspect, and then we drop columns that we will not be using, and just display the new data frame. We are going to change the indices to make them compatible with the COVID-19 data frame. So now the index for this data frame is actually the country. And next we're going to check the shapes for both data frames because we want to join them. And then we join both data frames. So this is our final data frame that we're going to use for the analysis. We'll do a correlation analysis to see how the variables are related, and then to better visualize that, we'll make a heat map. So here you can see the heat map. So once we have the joined data sets, we will do like simple correlation plots based on a single variable regression. So this is how the relationship between GDP per capita and the maximum infection rate looks like. And then we will draw a regression line. So there's a positive relationship. We'll repeat the same process for all other variables. And this is again just to inspect the data before we run the regression. So the next step is to import all of the libraries that we need to estimate the linear regression with all of the variables jointly. So we'll save all of our control variables in X as a list, and then Y will have the maximum infection rate. We'll check the shape to make sure that they're compatible. We'll estimate the linear regression, and note that we take the log of the Y variable. And then after that, we will extract and rank the coefficients for each feature from the linear regression. So as you can see and read from the description, healthy life expectancy and GDP per capita are the two most important features. And now moving on to the second part. We'll start by importing a battery of libraries that will be needed for data processing, visualization, but also to run the time series forecasting models. And then here we only need the death series, which we have imported earlier on. So we will just transform that data frame by first transposing it and then summing it row-wise. And then we will convert it to a list. And we'll create a new data frame with 2 columns. Then the next step is to get the dates from the columns in the deaths data frame, starting from the 5th column. And we'll save them as a string format. Then we'll do some additional data processing to convert the strings into datetime format, and then assign the dates and deaths data to the columns in the new data frame. And we will need to have only one data column, Y, with the index being DS. And finally, we'll plot the daily deaths just to inspect it. And this is total daily deaths in the world for the COVID-19 pandemic. And to see the daily increase, we will use the diff method as we did before. So this series is quite volatile, as you can see. And we are going to analyze the daily reported deaths. So like the first difference of this curve. And we need to remove the first data point here because it will be a non-value once we take the first difference. So the first model we're going to estimate is the Sarimax model. Here's a little bit of a description about the model itself. The initial step is to split the sample, which we will do based on a chosen date, which is July 31st, 2020. So now we have the train and the test. The next thing to do is optimizing the hyperparameters for the Sarimax model. There's 3 of them. So we need an ordered tuple. So we have the ordered tuple, and we will use those parameters to estimate the model. And then we fit the model, and finally we just draw a graph of the prediction. Pretty good fit. It does overestimate the deaths a little bit. And then we'll use the mean absolute error as a model accuracy measure. Now moving on to the neural network. This is slightly different, so we need to extract the independent features, and this is what we're doing here. And then we create a training and test model. There's different ways of doing it, but here we're going to use a cutoff date because that's more optimal. And once we've split the sample, we're also going to normalize the data using a standard scaler. And there's a description here of why we do that. And finally, we're going to train both XGBoost and the neural network model. So we train, fit the model, we calculate the mean absolute error, and then we create and train the feed-forward neural network model. Okay, and we compare the mean absolute error values for all 3 models. As you can see, the neural network model has the lowest mean absolute error, which in this case is 633. And as a final step, we're going to visualize the predictions from all 3 models, which is what we see here. So Sarimax performs pretty well, captures volatility, underestimates a little bit. XGBoost captures the volatility, overestimates the daily death toll a little bit. And then the neural network, even though it has the lowest mean absolute error, it extrapolates a linear trend. So there's ways of improving these models by fine-tuning the optimization and penalizing for overfitting the data. And there's other exciting avenues to expand this project using Spark streaming technologies, sentiment analysis, but also expanding the number of variables and the sophistication of the different types of models that can be compared in terms of which one is better at predicting both infection rates for COVID as well as death rates.